we illustrated the recursive structure of a binary tree, and don't forget about the 2 little exercises you were assigned to do. And one would be to turn the conceptual sketch of how to count the number of nodes recursively of a tree into Java. And the second one would be how to count or how to search recursively in a binary tree. Right? So both should be done rather straightforwardly by you into Java. Right? If you got any trouble, reach out to me. Otherwise, I will assume you're going to complete the exercises. Let's now move back. We are now going to talk about how we can organize the nodes in a binary tree into different levels. And which level a node should be in depends on its depth, meaning the distance, number of edges from the node to the root. Right? That's exactly how we calculate it recursively in the case of the general tree. In the case of binary tree, the calculation will just be the same. Remember, binary tree is only just a special case of a general tree. This is a very important diagram illustrating the different levels of a binary tree, starting from 0, and also the maximum number of nodes that could be in each level. But I would like to recreate this diagram from scratch and also derive some interesting mathematical properties together with you, which will be quite fundamental for your understanding for the later parts. Let's now do it together. We'll start with the root of the binary tree. Let's draw the root over here. And we're going to talk about 2 properties that we're going to derive. One would be, which level are we talking about? So let me put it down here. So it would be about the level, which would be some integer value. And for this case, for the root, is going to be 0. And the 0 over here corresponds to the depth of all the nodes at that particular level. Right? The level value basically corresponds to the depth of all the nodes at that particular level. The depth. And remember, by definition, the depth of the root of the tree will be 0 because you simply don't have any edges to go from the root to itself. And the second property I would like to talk about is the maximum number of nodes at that particular level. The maximum number of nodes at level whatever that we are talking about. For level number 0, we can only have just a single unique root. So that's why it will just be 1. Right? So far so good. It's a very good beginning. Let's now talk about level number 1. We're going to talk about the maximum number of nodes which can have the depth value 1. How many node maximum can we have? Basically, those nodes should be somehow connected with the nodes at level 0, which will be just the root. What will be the maximum case? In that case, the root node should really have the left child and also right child. That will be the maximum case. Agree? So I'm gonna draw that. So that means we got the left and also the right, right? And for each one of them, it will just be a node. So let me just copy that and paste it. So we got one node over here and also one node over here. Both of them actually got the depth value, just one edge to the root. So level number will just be 1. And what about the maximum nodes at a particular level? This will be basically how many nodes you actually got in the previous level. We got only the unique one. And then, in order to really reach the maximum case, it should have exactly 2 child nodes. So that will be 1 multiplied by 2. Multiplied by 2, which is equal to 2. You will see exactly why I'm trying to write in this way. We'll see. Let's now go on to level number 2. Now we want to talk about all the nodes where the depth value will just be 2, meaning that we should really get 2 edges to really go back to the root, right? What will be the maximum number? Well, so that means all the nodes at level 1 should have exactly 2 children. So that will be how we can create the maximum number of nodes in the next level. Agree? In that case, it's going to be just 2 multiplied by 2, which is equal to 4. So we now can predict there's going to be maximum number of 4 nodes at level number 2 with the depth value 2. Let's now try to do them. I think I'll do maybe up to level 3, and then we can make some conclusion. So I'm going to get 1 over here. I'm going to get 1 over here. And 1 here. Okay, and 1 over here. Right, we got maximum 4. And all these should be at level 2. And the left, and the right, and the left, and also the right. You don't necessarily have to really put the arrow over here. I just want to show to you, it's really about going to the left and going to the right. But when you visualize the tree, you don't necessarily have to put the arrow, right? It's not really necessary, but that's okay for now. And so that's about the maximum, right? So far, so good. The value for the level simply correspond to the depth of all the nodes in that particular level. And the maximum number of nodes, as we can see, well, we haven't seen the pattern just yet. Let me just do one more level, which will be level number 3. All the nodes at level number 3 are going to have the depth value being 3, meaning that it's going to take 1, 2, and 3 edges to the root. And how many will they be in the maximum? Well, in the maximum case would be for when every node at the earlier level, level number 2, every node there has exactly 2 child nodes. So that'll be the maximum criteria, right? So how many would there be? Well, in that case, we got 4 nodes at the earlier level 2. And then we're going to multiply each one of them with exactly 2 child nodes. So that will be 8. That's going to be 8. Let's now draw that very quickly. Let me just draw these 8 nodes very quickly. All right, done. And I'm going to put it here, here, and then I'll move the tree slightly accordingly, right? Just around the middle over there. Right? So the tree will become a little bit prettier. Okay. All right, so let's now draw the left and right link. So the left and the right, it could be prettier, but you can do that. But for now, we can live with it. And the right, and the left, and the right, and the left, and the right over here. So we got 8 nodes at level number 3. So what's really the pattern over here? Let's observe. In terms of the level, we got 0, we got 1, we got 2, we got 3. In terms of the maximum number of nodes at each level, so far we got 1, we got 2, we got 4, and also we got 8, right? Can you see the pattern over here? How can you relate each number in the pink with each number in the green? Can you relate it? Let's now talk about the pattern. Okay, if the level is simply, let's say, D, and the D is simply just a depth value for all the nodes at that particular level, right? Can you see that 1 is exactly 2 to the power of 0, and here 2 is 2 to the power of 1, which is 2 to the power of 2, and over here 2 to the power of 3. The exponents over there, not surprisingly, is exactly the level value over here. Agree? Right. Let's now go a little bit further. If I try to make this a more general tree, let me try to do that over here. So let me just think about the tree is going to be much bigger in general. Let's say this, right? And we only talk about level 3 over here, but it's going to go further, right? So let me move this a little bit to the left so I can just try to do a little bit more. Okay, this will be the entire tree, right? And you can see the level is actually going to go down all the way to the heights of the tree, right? Remember, the height of the tree, starting from the height of the tree over here, is by definition the maximum depth of the nodes in the tree, right? So in that case, maybe we still have some nodes at the maximum level, right? At least 1, right? So there may be some nodes over here, some nodes over here, and etc., right? At the maximum level. In that case, what would be the maximum number of nodes at level H in that case? Well, by definition, well, actually not by the pattern we observed, it would be 2 to the power of H. Agree? I think the reason that I really want to draw it from scratch, maybe it's easier for you to see exactly how to construct a tree. It's quite important. And then we can see that in the case where the height of the tree, if that's H, the maximum number of nodes at that particular level H, you can have 2 to the power of H. The next one, how do we calculate the maximum number of nodes when you actually have a tree with height H? In that case, what we got to do is the maximum number of nodes in a tree this will be the final formula we want to come up with. Everything we have done so far is really to prepare for the derivation of this formula. In a tree with height h, right? Just notice the phrasing over here. The maximum number of nodes in a tree with height h, right? So we talk about height 0, height 1. Sorry, we talk about depth 0, depth 1, 2, 3, all the way to depth h. We want to summarize, we want to sum up all the nodes over here. How many do we have in this case? Let's now put them into a sequence, like a series over here. It's going to be level 0, 2 to the power 0. So that'll be 2 to the power of 0 plus 2 to the power of 1 plus 2 to the power of 2 up to here, all the way to 2 to the power of h. And that's indeed a geometric sequence. And just for your background, you can simply go to this slide over here. This one reviews about the geometric sequence sum. And you can definitely just go click on this link. Remember, just earlier last week, we spoke about how we can derive the geometric sequence sum for our dynamic array analysis. You can definitely click on this link to really review that derivation. I'm going to leave that to you. And then for our case, you can definitely see this one as well. But let's now just go back, right? The formula is going to be, the initial term is simply 2 to the power of 0. So 1 multiplied by, and it's going to be, how many terms do we have in this case? First of all, the common factor is really 2, right? 2 to the power 0, 2 to the power of 1. Every time we are simply multiply by 2. So that's why it's a common ratio. Right, so let me just mark it down. So this part over here is really the common ratio. You will see that it's denoted as R in the geometric sequence. It's going to be 2 minus 1, and also the common ratio to the power of number of terms. How many terms do we have? We go from exponent 0 all the way to exponent h. So we got h plus 1. Right, it's really important to know that too. So we got 0, we got 1, 2, all the way to h. So that should be h plus 1 minus 1. That's the formula. And let's simplify it. It's going to be this part here, just be 1, 2 to the power of h plus 1 minus 1. That's really the final conclusion of this illustration over here. The maximum number of nodes in a tree with height h, from level 0, level 1, all the way to level h. The maximum number will be 2 to the power of h plus 1 minus 1. You ought to know about how exactly this number over here is derived. We're going to need this for many exciting properties that we're going to talk about in the later part for the lecture. Let me try to clarify some potential confusions you might have, which is about the shape of the tree. This part of the tree contains the nodes from level 0 up to level 3. But in general, the tree may be much higher, up to level h. So the way we can visualize it will be up to here, and then we can use ... to say the same pattern of maximizing the number of nodes at each level by multiplying by 2 is simply going to continue. So I think I can draw this slightly better. Let me make some very quick improvement. And over here, so we can have actually simply completely filled out all the nodes at this bottom level over here. So what you gotta imagine is, starting from level 3 over here, if we want to go to level 4, we're gonna make sure every node has exactly the 2 child nodes over here, right? That's something you want to imagine, okay? And I'm not gonna draw the circles over here, but I'm gonna put ... and dot. We're gonna continue with this particular pattern for all the remaining levels from level number 4 to level h minus 1. And at level h minus 1, every one of them, every node is actually going to contain, for example, some node is going to have this and this as a left and right child. And also the last node over here at level h minus 1 is also going to contain the left and right references to these 2 nodes, right? So that's really the more complete sketch you can kind of imagine. And of course, this part will be ... and dot. This is how you can visualize the entire tree, generally with height h. Alrighty, let's now move back to the slides. And so you can definitely go over one example about summing up all the nodes from level 0 to level 4, you can definitely use the formula about summing up the geometric sequence. Make sure you brush up with the formula and know how to use it. And this slide here is exactly what we just went over about calculating the maximum number of nodes in the tree with height h.